The weight of profound stillness settles around you now, a comforting blanket woven from deep indigo and velvet shadow. You can almost feel the slight, rhythmic pressure against your skin, a steady, muffled pulse that matches the deep, slow beat of your own breathing. There is the faint, clean scent of mineral salts mingling with the cool, vast expanse of untouched water. And if you listen very closely, you can perceive the minute, almost imperceptible rocking of the current, guiding your thoughts into a deep, tranquil suspension. Chapter 1. The Introduction to Vibration, the Anatomy of Sound. Slowly, we begin by considering the most elemental nature of sound itself, a concept so pervasive it is often taken for granted, yet fundamentally rooted in the simplest physics of motion. Sound, at its core, is not a substance, but rather a disturbance, a quantifiable vibration that moves through a medium. This seemingly invisible energy requires an intermediary, a physical substance, be it a gas, a liquid, or a crystalline solid, to propagate its existence from one point to the next. This mediation is critical, transforming mere energy into a palpable wave form that reaches us across unimaginable distances. To fully comprehend the whispers of sound, one must first observe the three defining characteristics that govern its passage: frequency, amplitude, and velocity. These three variables do not operate in isolation. They interact within a complex, beautiful system that dictates how and when sound arrives at an endpoint. Imagine frequency, measured in cycles per second, or hertz, Hz. Frequency is the measure of how rapidly the wave oscillates, defining the pitch that we perceive. High frequencies, such as those traveling above the upper limits of human hearing, suggest rapid, tight compressions and rarefactions within the medium. Low frequencies, conversely, moving at slower, deeper cycles, suggest vast, sweeping movements through the material, notes that resonate with the deep earth itself. Next, we consider amplitude. Amplitude relates to the intensity of the vibration, dictating the loudness or volume of the sound. A high-amplitude wave represents a massive displacement of energy, a powerful, forceful push and pull within the surrounding matter. Conversely, a low amplitude suggests a whisper, a gentle, barely felt ripple of existence. These measures are key to understanding not merely what asterisk sound is, but how potent it can be. And finally, we encounter velocity. Simply put, velocity is the speed at which the sound wave travels from source to receiver. It is determined entirely by the properties of the medium itself, the density, the temperature, and the elasticity of the material through which it is forced to journey. This variable, the speed of sound, is perhaps the most evocative, for it implies a direct, beautiful relationship between matter and unseen energy. As we drift into the complex geography of sound propagation, we will follow this thread of velocity, watching how the speed changes dramatically when moving from the airy expanse of the atmosphere to the immense, cold depths of the ocean, or through the structured, solid geometry of crystal. This steady consideration of constants and changes is merely a quiet journey through the nature of existence itself, a journey best taken in the stillness of approaching sleep. Chapter 2. The Aerial Passage, Sound in the Atmosphere. We now gently lift our awareness, moving away from the water's embrace and into the breathable, fluctuating expanse of the Earth's atmosphere. Sound traveling through air, a gas medium, is an inherently complex and variable experience because the atmosphere is not uniform. It shifts, layers, and changes dramatically with altitude and temperature. The speed of sound through air is not a fixed constant, but rather fluctuates proportionally with temperature. For every degree Celsius increase, the speed of sound increases by approximately 0.6 to 1 meter per second. This seemingly small mathematical relationship has profound real-world consequences for echolocation, for communication, and for the sheer physics of wave travel across continents. Consider the temperature gradient. In standard conditions at sea level, the speed of sound is approximately 343 meters per second. But if we ascend into the upper reaches of the troposphere, where temperature variation becomes more pronounced, the speed of sound subtly shifts, guiding the passage of sound in surprisingly complex ways. This alteration is what creates atmospheric ducting, phenomena where sound waves are bent and trapped, sometimes traveling much further than linear calculations would suggest. The troposphere, the lowest layer, is where most of our lived experience occurs, and here, the air is subjected to continual pressures of mixing, temperature shifts, and changes in humidity. The air density, therefore, becomes a fluctuating parameter, acting as a variable filter for the energy of the wave. Moving slowly upward, we enter the stratosphere. Here, the air is thinner, and the temperatures often change in a way that affects the wave propagation almost subtly enough to be missed, unless one is paying close, patient attention. The pressure diminishes, the molecular density thins out, and the mechanisms by which the air transfers energy, through elasticity and compression, are forced into a more rarefied state. This journey through the atmospheric layers is a masterclass in variability. The speed of sound is not given simply by the initial condition. Rather, it is modulated by the cumulative effect of countless micro-changes in temperature, pressure, and molecular grouping along the entire path of the wave. It is a lesson in acceptance of change, mirroring the gentle surrender we practice as our consciousness drifts deeper and deeper into repose. The wave energy passes, modified through the varying density, simply continuing its journey through the beautiful, restless medium of air. Chapter 3, Dipping Deep, Sound in the Ocean Medium. Now we allow our awareness to descend entirely, slipping past the boundaries of air and into the vast, cool embrace of the world's oceans. Sound propagation through liquid, particularly salt water, represents an entirely different set of physics compared to its passage through the gas of the atmosphere. The medium here, saline liquid, is massively denser and far more incompressible than air. This fundamental difference profoundly impacts the velocity of sound. Because the water molecules are much more tightly packed and highly elastic, they transfer the mechanical energy of the vibration much more rapidly and with less loss than the less dense gases above. The speed of sound in water is significantly higher than in air. By way of specific measurement, the approximate speed of sound in pure fresh water at 20 degrees Celsius is around 1430 meters per second. When we incorporate the salinity of seawater, this figure increases, generally settling to around 1500 meters per second. This increase in velocity is a direct consequence of the physical properties of the dissolved salts, which enhance the overall molecular cohesion and elasticity of the liquid medium. In the ocean, the speed of sound becomes a function not just of temperature, but also of pressure and salinity, forming a delicate triangle of influence that defines the oceanographic sound speed profile. The deeper we descend, the greater the hydrostatic pressure increases, and this increased pressure causes a marginal, yet continuous, rise in the elasticity of the water, thus slightly increasing the speed. When we consider the entire expanse of the deep ocean, we are considering a medium that is remarkably stable, a quiet, predictable curtain of water. Sound energy can travel far, sometimes exceeding 1,000 kilometers with remarkably little attenuation. This profound capability allows deep-sea life, and indeed human technology, to use sound as a foundational pillar for communication and understanding the immense topography of the seabed. A sonar ping, for instance, is a perfect illustration of this acoustic mapping ability. sending a sound pulse downward and patiently waiting for the precisely timed echo. The principles governing sound underwater, particularly the phenomenon of refraction and reflection at the depth of total internal reflection, known as the SOFAR channel, show us nature's elegant solutions to guiding energy. These deep channels act as acoustic waveguides, effectively trapping sound energy and allowing it to travel for thousands of kilometers, far exceeding the usual constraints of atmospheric physics. It is a profound demonstration of how matter can be structured, or how natural processes can structure it, to guide an ephemeral energy flow. The deep ocean thus becomes a vast, slow conduit, a silent, powerful testament to the persistence of vibration. Chapter 4, the transition zone, density and velocity variation. As we gently move between these different mediums, from the air to the water back toward the solid, we must pause and consider the point of interaction itself. The transitions between dissimilar media, such as air meeting water or gas meeting solid, are places of extreme physics, governed by complex rules of refraction and impedance mismatch. When a sound wave encounters a dramatic change in medium, its path and its perceived velocity can be dramatically altered. The concept of acoustic impedance, which is the product of the medium's density and the speed of sound within it, becomes our most crucial guide. A large difference in impedance between two media can cause a considerable amount of the wave's energy to be reflected back toward the source, rather than transmitted onward. Think of the boundary between the surface of the ocean and the air above. This interface presents a massive impedance mismatch. When a loud sound occurs on the water, a shipwreck, for example, a significant portion of that immense vibrational energy is reflected back, returning to the source, while only a fraction is transmitted into the air. This physics explains why sound dissipates so quickly when moving from the water to the air, unless the source is perfectly coupled to the boundary, like a floating hull vibrating against the water itself. These boundaries remind us that the journey of energy is not merely about continuous transport. It is about meeting resistance, about adjusting, and about understanding the precise interaction at every frontier. The elegant, unavoidable loss of energy across environmental boundaries is as important to the physics of sound as the successful propagation within a single homogeneous medium. It is a quiet lesson in loss and conservation. The entire system of planetary energy flow relies on these graceful negotiations. The slight change in density required for sound to travel across a mountain pass, or the perfect, predictable refraction required for a transatlantic communication cable to operate. These are moments of physical poetry, governed by the immutable laws of matter. We observe these laws not as boundaries, but as subtle guides, subtly steering the vibration toward its intended destination. Chapter 5, Through the Structure, Sound in Crystalline Solids. Now, if we guide our focus away from the fluidity of the air and the sea, and into the uncompromising, structured geometry of crystalline solids, the mechanics of sound shift once more, attaining a fundamentally different, highly ordered quality. Unlike gas or liquid, where particles are moving semi-freely in a crystal lattice, such as quartz or diamond, the energy of the sound wave is transmitted through the fixed, regular bonds between atoms. The material structure itself acts as the conveyor, dictating the path and the speed of the vibration with almost absolute predictability. Because the atoms are held in fixed positions and the bonds are of immense, predictable strength, the transmission of energy is remarkably efficient, with very low rates of internal friction or energy loss, especially at low frequencies. The speed of sound in a solid is typically much higher than in fluids or gases, varying depending upon the crystal structure itself. its stiffness, and its atomic packing arrangement. For pure quartz crystals, for instance, the speed of sound is precisely predictable based on the specific direction of the wave traveling through the lattice, displaying highly anisotropic properties. This means the speed can vary significantly depending on whether the wave is traveling parallel or perpendicular to the main axis of the crystal structure. This crystalline transmission is a beautiful demonstration of constraint transforming efficiency. The limitation of fixed atomic positions does not hinder the flow, rather it perfects it. The material itself dictates the law, and the wave simply accepts that law. The sound energy travels not by displacement, as in a fluid, but through the mechanical deformation of the bonds, the atoms momentarily pulling and pushing against their neighbors, a predictable rhythmic dance of energy transfer. The solid medium thus teaches us a lesson in perfection. That structure, when highly ordered and predictable, creates the most reliable and stable means of energy transport. This stability, this perfect periodicity, allows these crystalline materials to serve as foundational elements in highly precise scientific instruments, tapping into the purity of wave mechanics. Chapter 6, the mathematics of wave interaction synthesis. We now draw these disparate fields together, the gaseous atmosphere, the liquid ocean, and the rigid solid, to observe the overarching mathematical and physical principles that unite them all. Though the mediums are radically different, the underlying mechanics that govern the journey of the wave remain beautifully constant. The relationship remains defined by the equation relating velocity, v, frequency, f, and wavelength \lambda $, which elegantly states that v equals f times \lambda $. This equation acts as the master key, linking the observed properties of the sound wave, its speed, its pitch, and its physical length of vibration. If the speed of sound changes, as it does when transitioning from cool, deep ocean water, around 1480 meters per second, to warm, thin air, around 345 meters per second, then for any given frequency, the wavelength asterisk must asterisk change proportionally. A wave that traverses this massive difference in velocity will necessarily exhibit a corresponding expansion or contraction of its wavelength. The physics is flawlessly self-correcting, maintaining an inner harmonic harmony. Furthermore, the principle of energy decay or attenuation is a common thread. In the gaseous layer, energy loss occurs through molecular collisions and viscosity. In water, loss occurs largely through internal friction and scattering. In the solid, loss is mitigated but still present due to internal damping. Understanding these competing loss mechanisms is key to understanding the practical limits of sound transmission, whether through air, water, or rock. Pause. The synthesis reminds us that the seemingly disparate realms, the ethereal air, the dense water, and the solid earth, are all governed by the same fundamental physical laws regarding wave propagation. The medium defines the rules, but the rules themselves are universal. Pause. This continuity in physical law across different media is the most profound lesson. That nature prefers efficiency, finding the most stable and predictable means of energy transfer, regardless of the physical state encountered. Pause. We draw our final conclusion from this comprehensive study of wave physics, recognizing the universal elegance of the physical laws that govern the movement of sound, a humble yet potent messenger that connects the molecules of the world. Pause. The gentle sway of the tide, the distant rumble of thunder, the quiet hum of the earth, each is a perfectly orchestrated demonstration of physics in action, a reminder of the invisible yet persistent power of the wave, connecting every part of existence. Chapter 7, The Language of Life, Bioacoustics and the Living World. Having cataloged the physics of sound in its purest, most structured forms across air, water, and crystal, we now shift our focus to the single most profound manifestation of these principles: life. Biological organisms, from the smallest plankton to the largest whales, have evolved sophisticated mechanisms to interact with and exploit the medium of sound. In this realm, sound is not merely a wave. It is the language of survival, the architect of community, and the map of the unknown. In the marine environment, sound travels with uncanny efficiency. Whales, for instance, utilize extremely low-frequency calls, infrasound, which can travel hundreds, even thousands of miles through the density of the ocean. This acoustic communication allows mothers to reunite with calves separated by vast distances, and pods to maintain critical knowledge of migration routes across generational timescales. The frequency and rhythm of these calls encode complex information: identity, warning, courtship, and navigation. Contrast this with the high-frequency signaling of toothed whales, which use echolocation. This mechanism is a perfect illustration of sound's physics in action. The animal emits a controlled, high-intensity sound pulse and then listens patiently to the returning echoes. These echoes are not merely proof that an object exists, they carry exquisite detail. The time delay reveals distance. The frequency spectrum reveals size, texture, and even the behavioral state of the target object. It is a form of passive, three-dimensional seeing that transcends visible light. On land, the vocalizations of primates, birds, and even certain insect species demonstrate a remarkable evolutionary capacity for acoustic manipulation. Bird song, for example, has been observed to be far more complex than simple alarm calls. It often contains unique, signature motifs that function as reproductive advertisements or complex territorial declarations. This biological imperative, the drive to communicate, is governed by the physical parameters of sound: amplitude, loudness, frequency, pitch, and duration, rhythm. The common denominator across all these disparate systems is adaptability, the ability to modulate one's own vocal output to best fit the physics of the transmission medium, be it the dense, resistive atmosphere or the highly conductive saltwater, is what distinguishes successful biological utilization of sound. Life has not simply adapted to sound, it has learned to command its laws. End of Section 7, Introduction of Bioacoustics. Transition, moving from abiotic principles to life's interaction with sound. Midpoint refocus, the inherent connection between physics and biology. Imagining the next section needs to bridge the abstract physics with the complex life forms, emphasizing the measurable, predictable nature of these interactions. Pre-writing check. Need a strong transition to the final deep dive into complex systems, perhaps focusing on the measurement and modeling of these interactions. Self-correction expansion. The current structure is solid, moving from theory / writer-o-dollar biology. The next stage should formalize this by introducing the tools and mathematical models used to quantify these phenomena, bridging the gap to advanced engineering signal processing. Next section focus: advanced modeling and metrics of acoustic interaction.